Good evening and thank you all for coming. There will be other two speakers after me. They will also talk about the scientific aspects of music and sound in general. But being from Raman Research Institute, I thought I will talk about some of Raman's work on sound waves. He has done a lot of things, but I picked up a few things. If you look at Raman's work, I mean, we know about Raman effect, but that's something to do with light. But if you look at his work throughout his career, there's one theme that runs across his work, apart from other things, and that's the waves. The sound is a kind of wave, so is light. And he was, in general, curious and very fascinated by the wave phenomena, the different subtle effects of waves. And one of the things that he was interested in is the whispering gallery. I'm sure you have heard about some of the architectural structures. For example, we have in Karnataka, in Bijapur, Gol Gumbaz, and this is a picture of that. And this is Victoria Memorial in Calcutta. This is also a picture of the inside. And one of the most famous examples is in London, St. Paul's Cathedral. So basically, there is a circular rim kind of a structure, and if you whisper at one place, you can hear the sound even if you're standing, very far away on the opposite corner, and not just one corner, but along the rim. But I should warn you here, if you Google whispering galleries and the scientific explanation, you might actually end up listening to the wrong explanation. There are some YouTube videos which give the wrong explanation, and they say that there are two foci, the focus, okay, and if you whisper at one of the foci, then it gets focused into another foci. But that's not the case. It actually can be heard all along the rim. So it's not just a question of two centers. So those explanations, although there are lots of information in the internet these days, one has to be very careful about what you get. And so now this is one of the papers that Raman, this is the first page of Raman's work in 1922. So he mentions the Gol Gumbaz and Victoria Memorial. Also there's a structure in Patna, the granary, the old granary, which is also like a dome-like structure. And he goes into the architectural, the dimensional details of all these structures. Now, there was an explanation at that time when he wrote this article in 1922. There was an explanation going back to Lord Rayleigh. Lord Rayleigh, those of you who have studied physics, a lot of things about waves that we know go back to Lord Rayleigh. Okay, and so Lord Rayleigh gave an explanation in 1878, but Raman had found some problems with the explanation because he did some experiments in London, in St. Paul's Cathedral, also here in Gol Gumbaz and in Victoria Memorial, where he found that there are some discrepancies there, and he was not quite satisfactory. And so he set out to find out the real reasons. Now, to understand what's happening, one has to think of waves in general. It can be water waves also. So suppose you take a bathtub and you make a partition, make it into divide it into two halves, and make a hole in the partition. Excite some water waves by doing something, disturb the water waves and create ripples there. And if you inspect what's happening on how the waves go through the hole and how it goes into the other half, you'll notice that they can spread out. In scientific jargon, we call it waves can diffract. Okay, I'm not going to use any jargon, so those who are scientists here and the science students can pardon me for not being precise enough. So I'll just say that they spread around. Okay, and the amount of spreading, the angle by which they can spread, depends on two things. One is the size of the hole and the wavelength of the whatever waves you are exciting. If this ratio if the size of the hole is small compared to the wavelength, then the waves are going to spread out a lot. So, as you can see here, so they are going to spread out. Okay. Now, for light in general, the wavelength is very small. This wavelength is very small compared to the typical hole sizes of objects that we encounter in daily life, which means that this ratio is very large. If denominator is small, the ratio is going to be large, and so it is not going to spread out, and this is why we are taught that light travels in a straight line. It does not spread out much. But sound wave, but if you can make a hole which is small enough comparable to the wavelength, then you can see the wave effect, the diffraction effect of light also. But this is usually seen in, for example, sound. For sound waves, the wavelengths are comparable to the sizes of apertures, the size of a door or window, and so you can see then the waves can bend around, they can spread, which is why if somebody is whispering or saying something behind me, I can hear. Whereas if somebody shines a light, I won't be able to see, right? It will not to pass through me. It's not going to bend around me. So, but then when you whisper, the frequencies that you excite, it's such that the wavelength is of the order of a few centimeters. Okay, that depends on the sound, the speed of sound in the air. But the bottom line is that when you whisper, then the wavelength is of the order of a few centimeters, which is comparable to the size of our mouth aperture, which is why it doesn't spread around much. Okay, so when somebody whispers behind you, you can't really hear, but if somebody speaks loudly, then you can hear because the waves can bend around. Now, so when we speak loud, then the wavelength can become 10 times larger, or the frequency is smaller, and so you can hear them. Now, what Rayleigh thought was happening is that when you whisper at a point, then the sound waves is confined. Okay, it's not spreading around. It doesn't spread. It's confined to a small cone. Okay, and those waves can repeatedly get reflected and then can come back, and you can hear at different places. Okay, that's what the explanation by Rayleigh. And he thought that the whispers can become trapped along in a layer close to the wall. And in 1910, then he did this again, and he compared to the effect of vibration of a circular membrane. He was working on the mathematical description of what happens in a circular membrane. We will come back to this later in another context. This is, by the way, one of the best articles that you can read on whispering galleries in Scientific American, going back to 1978 by Joel Walker. So, the Resnick Halliday has a third author now, Joel Walker, who used to write a fascinating series called Amateur Scientist. And this also talks about how one can do some experiments, simple devices in. So, you can read that. And so, what Raman found is that the intensity of sound along the ring is not constant, as Rayleigh had predicted. There are places where the intensity is large, where the places where the intensity is small, and they alternate. This is what he found, and that is so he thought that there's something else is happening there. He came back to India. He had a student named Vidibhushan Ray in Calcutta, and he asked his student to do an optical analog. Sound waves, he can do the light is also a wave, so you can build a whispering gallery for where light can whisper, right? So Vidibhushan Ray actually did that in an experiment. This paper came out in 1922 in Bulletins of Calcutta Mathematical Society. It's very hard to find these days anyway, but internet has everything now. So what they found is that there are places, alternate places with darkness and light, similar to what Raman had found for sound. There are alternate places where you can hear and not hear, hear and not hear. So this is sort of visual description of what is happening. So what Raman then found is that they are getting reflected, the sound waves are getting reflected from different places, but the reflected rays, so these two waves, when they come to some arrive at another point, they can either add up or they can cancel one another, okay, depending on the geometry and where you are. Okay. So it's called the interference. I mean, you can either add the waves or you can cancel out the effects of the waves, right? So this is what, and this is the paper that he wrote in Nature, the letter to Nature, and right. Now, interestingly, the story doesn't end here. Raman was also interested in other things, among other, I mean, like natural phenomena. He was probably one of the last, what you call the, natural philosophers, curious about what's happening in nature. So he was also interested in pearls, in gems and other things. Pearl is very interesting. Pearl has layers of small crystals and is stratified. And so he had written papers in, on structures of pearls. Now, it turns out that many years later, from my institute, Raman Research Institute, it was later shown that the pearl shines in a unique manner, just like it's like an optical analog of whispering gallery. It's light getting scattered in different along the layer. So when you shine a pearl from say at one spot here, the light it's not dark everywhere else. You can also see the illumination there, and that gives the pearl its unique sort of. So this is the optical counterpart of the acoustic whispering gallery effect, and this paper came out. This is in 1990s, late 1990s, from Raman Research Institute. And whispering gallery, as I said, it can. This is a wave phenomena, and any different kinds of waves would will show this effect. Even earthquakes. So sometimes. Earthquakes, there are waves, and you can think of the whole earth as a whispering gallery. And it has happened, for example, 1960, a strong earthquake in Chile. Apparently, the effect was seen, felt around the globe for about 3-4 days, and there were intensities going up and down within a span of few hours. So maybe this interference effect in different places was happening there. We now, astronomers now see these sort of effects in stars. This is it's a theoretical picture of what's happening in the sun. So these are like sun quakes. Same, it's like a whispering gallery effect. Okay. Now engineers use these effects to detect defects where it's very difficult to identify some of the defects. For example, there's this interesting story about US Air Force C-141 in 1990s. They developed a snag. Maybe some hole in the wings had some defect. It was very difficult to find where the defect was. So what they did, they excited some waves and then found whether there is an interference pattern along the rim, and that was very easy to find out where the defect was. So now whispering gallery is being used by engineers as a sort of a sensor. Okay? This is a very interesting article that you can look up. This is in Physics World. And this talks about all these phenomena. So it's out in, it's written for general public. So to end with, I just thought I'll talk about Raman and his, the tabla that you have seen in the exhibition. And you must have seen the sand, the small particles, grains that they have put in there to excite different modes. So Raman was also interested in sound and the difference between the uniqueness of Indian instruments, and he set out to find out what sets Indian, say, percussion instruments like tabla, mridangam, different from the Western drum. And so in one of his papers in the introduction, he writes that in all the instruments of percussion known to European science are thus essentially non-musical and can be tolerated in open air music or in large orchestras where a little noise more or less makes no difference. Indian musical instruments of percussion, however, stand in an entirely different category in its tonal qualities. And he wanted to find out what they are. So, so he worked on tabla, mridangam. So as you know, in a string, right, one can, if you pluck a string, you can excite different kinds of vibrations, different patterns of vibration. So one is the fundamental mode, but you can also excite these what are called the harmonics, right? Those are also going to be excited in different proportions, which will create different timbres, like timbre, right, of the tonal quality of the sound. So just like that, in a circular membrane like the tabla, the drum head, you can also excite different modes. Interestingly, so again we have to, Lord Rayleigh had his explanations, just like the whispering gallery thing. So this is a picture of the different, different modes of vibration that you can excite in a circular ring. Okay, these are the nodal circles where the effect is, so these are nodes. Okay, these are nodes where it's not moving, and these are the antinodes where the amplitude is maximum. Okay, so so these are the different nodal circles. I mean, so you can excite all these things, and these are the frequencies in relation to the fundamental mode. Interestingly, as you will see that the frequency ratio is not integral, in the sense that if I take the ratio of this to this, it's 1.594 to 1. 1.594 is cannot be written as a rational ratio of integral multiples, and that makes it very non-musical, because we know that if you want to if a sound has to appeal musically to our ear, the frequencies have to have an integral ratio. For example, sa and pa, the frequencies have a ratio of 3 to 2, 2 to 3. Okay, or sa and re, for example, it's it's the other way around, 8 to 9. Okay, sa and ga, it's 64 to 81. That sounds better, musical, and some aesthetical appeal in our ear. And if you don't have this integral ratios of different modes, because you're exciting different modes of vibration, it's not going to sound very musical, which is what Raman had figured out. The Western drums, they sound very non-musical. And you put this, what's called the siyahi there, right? The loaded in Indian tabla or mridangam, and this loading is done very, very carefully in a manner that, so these are the modes, 6 modes of with the fundamental that Raman had excited, and he goes into great detail explaining how the different modes can be excited, and he puts the sand grains right after exciting them and showing that. So, and these have the integral ratios, and so they sound very musical. They have they appealing to us. And there are lots of details about, for example, tabla and mridangam, you have this rim there, right? What are the effects of that? And in the left hand side of the tabla or mridangam, right, the loading is not in the center, it's slightly off center. That also has an effect. And he talks about all this. Then he talks about, for example, what's the difference between guitar and veena. So in guitar, for example, this is the structure of the bridge. In guitar, it's almost like a very sharp blade, where in veena, it gradually tapers off. So the string is like a tangent at some point to the bridge. That he sort of conjectured. He never came back to this later with any greater detailed work, but he said that there's probably a transfer of energy when you pluck a string there. It's transferring some energy to the bridge, and the bridge is this transferring energy back to the string later on and exciting other harmonics, which makes it very rich in the tonal qualities. So yeah, I'll stop here. So this is, I mean, some glimpses of Raman's work on Indian instruments and sound in general. So this, by the way, this work on the Whispering Gallery, the optical analog of Whispering Gallery, that was his first work with light. After that,
so my talk is going to be on creating music. I'm a professor at IISc, so I belong to the Division of Electrical Engineering and Computer Sciences. So I will talk to you about how to create music and artificial music synthesis and things like this, which is a different part of riding the sound wave. So when we understand music, right, what constitutes music, right? There is melody, which is arrangement of musical tones that we perceive as in the foreground as one entity. And then there is a rhythm, which is basically cyclically repeating beats or patterns, right, and this is in the background. Then in Western instruments and operas and things, you find this harmony, simultaneous use of 2 or more tones. Then there's dynamics, intensity, and volume of sound production, right? And otherwise, it's going to be very monotonic to listen to, right? And then timbre is the quality of musical tone. And how many of you, when you have sat through a musical concert, right, when they tune the pitch, right, you understand that it's not the same. The mridangam is also tuned to the same shruti or kattai, right? And then you see that the violin and the mridangam and the vocalist, though it is tuned, it has a different kind of quality, right? So, and that's characteristic of the instrument. So they are just not impulses or frequencies that we think of, but sort of a range of frequencies within a narrow band pass. And texture. Texture is the overall quality of all of these, these objects that we have, that we perceive as one entity, right? And information is very rich when we think about it, right? It's just not melody. There is rhythm, which is correlating to the melody. Then there are other, many other things, right? So all of it is rich content and information. So music is a form of communication using pleasing sounds and silence. This is very important because silence is an integral part of music. I mean, you cannot just keep emitting notes all the time or playing the drum. Sometimes you pause. It's a form of communication, right? When you sit and listen to a song, any song, I mean, some people pay attention to the lyrics, some are happy listening to the melody and things like this, but you have to also understand in the background, these are musical notes and rhythms and things which are all happening, and those are coded patterns, okay? So we'll see this in a while. So from the Indian context, so we have this shruti which is called the fundamental tonal pitch, which we call kattai. This is the sa and the pa, they form the invariant perfect fifth. The gamaka is, these are ornamented notes or inflections. There are, there's a documentation of all of these gamakas like quavers and shakes and stuff like this. When you talk to musicians, I happen to be a Carnatic vocalist, so therefore this sort of gets into what I see. It's much easier when I say, for example, when you say sa re ga ga ga, like re na na ni, oscillations there, ga re ga ma, things like that. Ma is plain note, ma. So you see these gamakams, when you play through the veena and things like this, you have that effect. You see that. And this is a Gayaki style or something, or this way that you can, or vocal cords can produce this. These are all ornamented notes. And so what is raga here, right? Raga is basically an abstract musical object which has all these gamakams, these musical phrases and everything else that you can weave out, right? Now when a composition is set to a particular ragam, then you are blending the lyrics and these notes and everything together. But if you extract the notes themselves, they're encompassing these gamakams and then musical notes, right? Bhava is the emotions where we talk about modulations and things like this. Tala, of course, I described to you that these are beats set to a count, okay? So how many of you here do not have any idea about music, tala and raga and things like this? So I can, okay. Tala is a beat structure. Re ga ma ga ga re sa ni sa re ga, that click beat, right? 1, 2, 3, 4, or 1, 2, 3. There are many 175 talams, okay, totally. So it can be p-adic. It's not necessarily dyadic, like 2 counts per beat. Sa re ga, 3 counts. Sa re ga ma ga, 5 counts, so on and so forth. It can be p-adic. Now, when you look through these musical tones and things, Bhiman mentioned about the Shadjam and the Panchamam and talked about this ratio of 3/2. This is here, Panchamam. Sa pa sa is 1 octave, okay. The Panchamam is exactly at this point, 3.2. And our system beautifully has these notes and all of these sir, is Shuddha Rishabham, sir, re, ga, things like this. You know, you have variations between Rishabham, Gandharam. Madhyamam, we only have to Sarigama, Sarigama, Shuddha Madhyamam, Prati Madhyamam. Two Madhyamams will I think divide the set of Mela, 7-tone majors, into two halves. And this is very interesting. And I'm not going to talk about the Katapayadi Sutra, but those who are interested, we can talk about this. It's a lexicographic way of arranging these notes in a way, in such a way that you can kind of take the ragam name and you can come up with the number in which it is arranged in the lexicographic order. I'll talk about this, but not get into details of the sutrams. So there is a ranking here for these notes. So now, you know, this, Sarigama Padani, I just took the Shankarabharanam. There are many Sarigama. Sarigama Padani. This is also one of the ragams, 7-tone major. Like this, you can go all the way from order 1 to the 72nd Melakarta Raga. Okay, and this is all documented by Sarangadeva way back in 13th century. So now, some common knowledge. I think this is a great instrument. Nowadays, we all have Shruti boxes because we cannot carry this. So this is a this is a tambura, which is a great instrument. And when you tune it, this is you tune you can adjust the length of the string, and you can get your pitch set. So now today we have all these D sharp, C sharp, blah blah blah, and we have to get to that exactly, right? But if not, with this instrument, say you had a bad throat that day and you were setting to a lower octave, this is analog in nature, and you can tune the metronome the way you want. Okay, and there is also this Jioala here that you observe. This is just another frets with these small. They have this using this woolen kind of small pieces. They connect, and by adjusting, you get that fine resonance. Okay. So now octave is basically bass, shadjam, sa pa sa doubles the frequency. So within that you have all these Rishabham, Gandharam, Madhyamam, Panchamam, Daivatam, and things, and then musicians are supposed to go 2 octaves up and down. Okay, so now you should know that a tone, a note, a swara that I call it, is not strictly a frequency or just an impulse. It's just not one sine wave, right? It has it's a narrow band pass signal which has other frequencies. Like I said, and I'll show you with waveforms how these are. Okay, so this sort of sets us to some common knowledge of this, and then the South Indian classical music, as I told you, has this, from the set of all the notes are there here. There are certain notes that are forbidden from pairing. For example, this Rishabham R2 here, this is Chaturthi Rishabham, doesn't go with Shuddha Gandharam and things like this. So those are few, and these are forbidden sets, and these are forbidden because they are accorded the same ranking in perceptual closeness, and in some cases when they are paired, they give you a discordant kind of hearing feel, listening feel. So therefore, you basically remove these combinations, and when you work out the math, right, the 3 combinations here, you would think it's 3 power 4, but it is not. But because of the forbidden sets, it's going to be 3 square times 2 cube. So you do the math, it is 72. That's how we have 72 Melakarta ragas. Okay, and each of them are named 1 to 72, and then there is a name for all these ragams, and I'll get to that real quickly. And this is how the Melakartas are labeled, from Kanakangi all the way to Rasika Priya, and they are given names, right? And then there is a sutra which is called Katapayadi Sutra, which basically takes the first 2 letters, Ka, Kanakangi, Ka, Na. It takes that, and then it has that number 1 you can arrive at using the sutram. Similarly, for Ratnangi, Ra, Ta, you can get the label 2, things like this. So, it is really beautiful hash function, and you would say that modern computer science had all of these, they discovered hash functions, you should go back. This is evidence dating before that which says that people had these sutras which are hash functions. Okay. And these are is beautifully divided, and you have totally about 12 chakras and within chakra and across chakras the nodes differ by 1 or 2 at most. And it is very interesting, and this is like the gray code, and those of you in computer science know about gray codes and how these are useful for decoding and things like this. This is a sort of a pseudo gray code, 1 to 2 nodes differing code. Okay. So, now as I told you why this is a form of communication, because if you take all of these nodes, now you have 7 possibilities in 7 tone major, you just take in 1 octave, just log 7 to base 2 is approximately 3 bits. So, you can communicate information using these nodes, and this is really interesting at the heart of why it is it could be music can be used for communications. So, what we did is we have all these things in mind. So, we tried to build a layered graph representation model for music synthesis. Our goal was to synthesize music. So, of course, the grand goal is, let us say MS Subbulakshmi has to come alive, right? There are certain compositions that she has not rendered or certain ragams she has not rendered. Using all the information that is available can be get to that. That was the kind of grand goal. It's still the grand goal, but with this question we were trying to ask the question, how can we synthesize melodies, and I will demonstrate the melody construction. So, it's very simple. If, for example, if you think about, let us pick any scale, anybody who who is a musician here or musically inclined that some ragams, anyone in the audience? You want Shankaravarnam itself? Okay. Same thing. Sa re ga ma pa da ni sa ni ra pa ma ga re sa. So, sa re ga ma ga re is 1 note or 1 swara per unit time. Sa re ga ma ga re, double speed. So, what happens is you can make transitions across layers. So, now when you think about how musical notes are connected, you don't like sa ni is very rare transition. Sa re ga ga, when you are at ga ma ga re ga ni, sort of the transitions you formulate those transitions which are appropriate, and then you weave out these. So, you have interlayer transitions and intralayer transitions of notes that are where each layer is characterizing the symbol duration in time steps, and therefore you can construct this sort of object here. Okay, so this is what we try to synthesize. This is machine sound. Okay. So, and one could visualize the emission of these notes as sequences like this. Okay, when you take a musical text, you will see these type of notations for your compositions. So, one could also notate the emission of the notes in this manner, where an underline here is showing that it is increased in frequency by 2, and this is 1/4 time step duration. Okay. So, I will go to the other part, which is basically synthesis for rhythm synchronization. So, we can also kind of synthesize the melody and rhythm together, we can blend them together. So, we can create these patterns, and here is how one could do this. So as I told you, these are the contours of the gamakams, and Kampita has these oscillations. Yeater Jaru can kind of oscillate from a lower note to the higher note and things. And what musicians talk about contours in a creative way, one can actually visualize these waveforms in this manner. Okay, and here is an example of how you can think of. This is the Nilambari gamaka, and the madhyamam. The waveform is gama. It oscillates between ga and ma. Okay, this is ornament that I was talking about. So similarly, we have other gamakams, and one of the interesting things in music is perceptual scale equivalence. And I'll say that, for example, you can take sa ri ga pa da sa da pa ga re sa, and then you can shift the graham from sa to re, and then you can completely hear a different note. Ri ga pa da sa re ma pa ni sa, things like this. So depending upon where your reference is, you can hear this way or the other way, and this is a nice group structure. And those of you who likes to know about algebra, I think you can appreciate these structures. Okay, so you can extract pitch trajectories for ragams and things like this, and you can actually extract a metronome frequency, and this is all fun stuff. So basically, getting the information from the musical clip, you can actually weave out a lot of information regarding the frequencies and things. So, I mean, these days people talk about AI. So we also have AI-based music synthesis. I'm going to play one snippet for you. We trained this using LSTMs, and this is fun stuff. I hope this works. Let's see. So things like this. So in the interest of time, maybe I should stop this here. So machines can create music. Machines can create text. Machines can do a lot of things. Machines can prove theorems. Okay, we are at this stage. And music theory, physiology, psychology, and physics are all interconnected. And this is where science meets arts, and you require mathematics to explain this. And this is precisely that. I didn't talk about any equations, any theorems. You can look into the paper for the details, and those of you are interested, I can share more mathematics inside that. There's heavy math inside that actually is producing all of these. But for in lay terms, it is just this is all machine made, machine synthesis. Okay. Few things to note. Information is additive. Thicker the musical texture, more the information content, and having semantic meanings can give you a lot of information to what we sense from music. Musical sequences are essentially coded patterns from a musical scale. This is something to be noted. Genres are culture dependent, but classical music is the basis of all of these, because we stick to a scale, and then with that you can kind of mix different scales, and that's how you can have film music and things like this. And that is why it's called classical, because you stick to the rules. So future could be genre, musician, and composer centric synthesis of virtual reality based musical concerts where you have bots playing music for you. Okay, so with this I end my talk. Thank you.
I wish Professor C.V. Raman had set his mind to so many decades ago. Because I'm sure with his, with the ingenuity that he brought to many of his studies, whether the Indian musical instrument or so many other things that he had done, I'm sure we wouldn't be breaking our heads over this problem of the allegedly musical pillars which exist at this temple called the Vittala temple at Hampi. I'm sure most of you know where Hampi is. It's the capital of the empire, the Karnataka Empire, which ruled a large part of southern India between the mid-13th to mid-16th century centuries. And in 1565, when the so-called Battle of Talikota happened and the empire collapsed, and then everything, the capital city was left in ruins. They abandoned it. So to start off, let me take you away to Hampi. So I'm sure many of you have been to Hampi, and those of you who haven't definitely must go to Hampi. The first thing that you notice in Hampi is masses of boulders. They basically have these plains and granite inselbergs. Inselbergs are basically just these large upthrust areas of granite, and they're all very much boulder strewn. But granite is basically a plutonic rock, as geologists look at it, because all this granite was under the ground at one point of time, and this molten rock cooled under the ground relatively slowly, and so granite has relatively larger crystals. So it's notoriously difficult to carve, for example. Like if you look at your Hoysala temples, the kind of finishes that you get there, the kind of detail that the sculptor can bring out in schist, which was used there, cannot be done on granite. But still, and it also shatters. When you apply the chisel and hit it, actually shatters. So a granite sculptor has to be extremely good at bringing out the kind of sculptures now that you will find in Hampi. So this is probably one of the reasons why when the Vijayanagara was founded, the artisans came from Tamil Nadu, because in Karnataka mainly sculptors are working with sandstone and schist and softer rocks like that. And so whereas in Tamil Nadu, right from the time of the Pallavas in the 6th century, people have been using granite. So their experience with granite was probably more. Maybe that's the reason why a large number of artisans from Tamil Nadu had come here. So we'll be directly going on to the Vittala temple here. So this is a view of the Vittala temple from across the Tungabhadra. So you can see the thing massed around here and the dramatic backdrop of boulders that you see here. This is yet another view of that. And this is a view at sunset. And the Vittala temple is supposed to be the climax of Vijayanagara architecture. So what started in a small way in the mid of 14th century, and then while we don't know when exactly the Vittala temple was founded, people kept on adding on bits and pieces to it till the entire complex came about. So it's supposed to be the architectural climax of Vijayanagara. So now, without further ado, I'll just show you a couple of these so-called musical pillars. Then we can have a discussion about what they look like. So you can judge for yourself whether they are actually musical. I wish we could increase the volume somehow. So many of the columns go by different names. This one is called the Jaltarang. And there's another one. So this is Mr. Ali of the Archaeological Survey of India who's playing these for us. And this is again I'll let him do the explanation for that. So he's talking about the columns on two different sides of the same, the pillarets on the two different sides of the same column. And then he goes on to the other side and places the two columns on the other side also for us to hear. That's a very familiar note, I guess, for most of us. So he calls it the school bell and the temple bell and the calling bell, but whatever it is, we can make sure that it is emitting two kinds of notes there. So as I told you, the Vittala temple in its current condition, it stands like this. This is the famous stone chariot, the shrine to Garuda, because, okay, in in the front that you can see here, and the temple is ruined because the mantapa is ruined, and I'll just show you a way of an aerial view of how this whole structure looks like. So this is the Tungabhadra river, and the temple has come here. So in the some people speculate that in the 14th century itself there was a small shrine to Vithala, which was later on added to by the different rulers. So we don't know when this nucleus came about, but we know that certain other things, like for example, we know that the Gopuras came about by two of Krishnadevaraya's wives in 1513 maybe, and this mantapa was added by a very important official in the Vijayanagara court called Udagiri Timmaraju in the year 1554. Now one of the things people say about is that Vijayanagara has been very wonderfully recounted by many foreign travelers who have come here. How come they have not mentioned these musical pillars? One of the reasons could be that it was this mantapa was added only in 1554, and by 1565 we had the Battle of Talikota, and the entire mantapa was ruined. So this is how it looks like in the plan. So this is a Vithala temple complex, and then you have this Rathabidi, or this with the this colonnaded street where we had shops and all that, like a bazaar in front of it. This is yet another view of it. So you can see that this is the mantapa that we are talking about, which was added in 1554, which has the supposedly musical columns, and this is a plan of it. So this is a shrine at the nucleus, at the center of the whole, the focus of the whole thing, and it has got an ambulatory around it. So this part and this closed mantapa, the Gudha mantapa, was existing earlier, and this is the part that Udagiri Timmaraju added with 56 pillars here. This is how it looks like now in its current ruined condition. And yeah, so these are the 56 pillars that you have here. And so just to refer to them, we can give an alphanumeric thing. So this would be like A2 and stuff like that. So you can refer to each of these pillars individually. But the problem here is that when in 1565, when the Vijayanagara kings lost the battle to the Bijapur Sultanate, and the Deccan kings, they looted the place. So what you see, this is not the mantapa, this is the Mahamantapa that you can see here. So, all said and done, even destroying a temple mantapa is a tough job. So what they did was that they heaped firewood along the main axis, where you go on, look towards the deity and then set it on fire. So these are scenes of how the thing looked like after, sorry, I went the other way, of how it looked like after destruction. There are two views taken in the 1800s. So you can see here that the roof has collapsed. Many of the columns here, this one is considerably damaged by fire. But when you go away from the axis, many are reasonably intact for us to study. So column number, G5 is a stump, only is left over. G6 is completely disappeared, and ASI has put a brick pier to support the areas there. Some of them show a lot of, this one is spalling, as it is called. When you apply fire to granite, the bits of it just fall off, which is called spalling. And so none of these can be studied, because you can see this one also. It's kind of obscured by the piers that was constructed by the PWD before ASI took over. But then there are some which are reasonably intact here. So this is a plan of the column. So generally the column has a load-bearing area, which is the one which takes the weight of the roof and all that. And then you have projections, which here there's one little colonnade which comes out. There are these two colonnades that you can see here, which project out of it. And here you have a deity, in this case Narasimha, that you can see here. So the whole thing, the whole contraption, right from the base till the bottom of this capital that you see here, everything is carved out of one piece of stone. So that I had estimated that maybe the smallest musical pillar like this, which had only 4 columns, it would come to around 6. The original block from which they carved it would come to around 16 tons. And the largest one, which has around 16 colonnades, would come to about 32 tons. That is the kind of weights that they dealt with. Okay, and so this column is this particular one that you can see out there. So I'll just show you some. Okay, before that, how did this musical this is called a composite column, because you got the main column and then you have the little bits and pieces projecting out of it. So it came from Tamil Nadu, actually, this concept. So if you look at a temple like Dharasuram or something, Chola temple, which is pre-Vijayanagara, you have the load-bearing portion and a little pilaster kind of thing projecting out, like you can see here. What happened is that when these people came over to Vijayanagara and started improving upon their earlier ideas, the pillarette actually comes clean out of the load-bearing mass, and it's carved completely in the round, as you can see here. And it has this basal portion, then you have you have 4-sided portion, then an octagonal portion, sometimes even a 16-sided thing, and then at the top you have this floral thing. There's a Amalaka-like thing, and then there's a Padma or a lotus-like thing which is projecting out. Interestingly, Dharasuram, the Airavateshwara temple, also has these steps which are unfortunately imprisoned now in this ugly cage-like thing. So there are the 7 steps which are supposed to be musical. I haven't seen that, I mean, in action at least. So this composite column that I showed you in the previous slide, it came to Vijayanagara the first time. It was exhibited in this Virupaksha temple complex, which you can see here. Virupaksha is the presiding deity of Vijayanagara, and so this is the Virupaksha temple complex. Like the Vittala temple, this was also added on. It's a composite structure added on in subsequent generations. So here you have structures like this which show only a bit of the pillar projecting out, and you have like this where it has completely come out, and all these things are extremely well carved. I want you to notice this fact so that we can compare it with Vittala temple, and most of them are identical. The sizes of all these things are identical, and they produced here. Where, so you can see closer up how well they have carved, even though they are granite and all that. You can see all these lines. The Padma is also well carved, and all columns have got identical size and shape in the Virupaksha temple, but not so in the Vittala temple. So what you see here, you see these 2 columns on either side of this load-bearing area. They have the same base, but they have different heights. So that looks very inelegant. Especially, I'll show you some other examples where it is even more inelegant. So you can see here, and we're talking about the monument that is the climax of Vijayanagara architecture. So why were they so careless about it? So you can see that in the same row of columns, there are 2 distinctly different heights. So you know that when you change the length of the string which is vibrating or the height of the column which is vibrating, you can change the frequencies, right? And you can see that the finishes, when you saw in the last slide when I showed you the Virupaksha temple, this is very crudely finished. Again, some few more examples I just run through. This again you can see the same called E4, and you can see that the columns on different sides are of different heights. And in this case again you can see that the columns are very different. It looks very, visually it looks very inelegant, and in this case it's even worse. You can see that the vertical, the abacus or whatever on top of it, it has moved away. It looks like a careless mistake, but I rather think that it is not. There's a closer view of the same thing which you can see here. I mean, by the time the Vittala temple was sculpted, the artisans at Vijayanagara were capable of producing wonderful pieces of architecture. Why would they make a simple beginner's mistake like this? And then you have these things where you see the Padma is of different sizes and different things. Somewhere, you know, it's not even very properly carved. Some places it's very crudely carved. And the masses there are differing. So you can see here, again in this, you can see the sizes are different. Some of them are very small, some of them are carved, some of them are not carved. Here you can see something which seems to be completely shaved flat. There's hardly any lotus there, isn't it? It's almost flat. Whereas some places, they're just lumps of rock there. So they've kept it there, so the mass is... So, and one more thing you'll notice is that the base here, though they're very close, somebody has taken care to separate them. Whereas in other places where the same kind of columns have been employed, like in this place called the Virupaksha temple itself, and in this Veerabhadra temple at Lepakshi, which is also a Vijayanagara temple, you find that when the bases are close by, they're fused. They don't bother to actually separate them. So why did they create this tiny little thing, maybe to separate the masses out or whatever? And then also they experimented with the cross sections. All of them are not square, all of them are not round. Some of them are turned squares, like you can see here in this particular column, which is I7. Okay, and here again you can see this one is a large mass of rock there. And you know that the cross sections are also important when you're producing rock, music or any sounds from a particular thing, because the way the torsional waves go across will be different in different cases. So, and also what is important is that this is another structure which has composite columns. It's called the Kudire Gombe Mantapa. It's actually on the way to the Vittala temple itself. So you can see here that the positioning of the columns has a kind of an architectural logic. So here, it starts from here and goes around like that. Here you have only one colonnade, and this is a corner where the plinth turns around like that. So you have these 3 columns defining the corner like that. And then you have these vyalas coming here, and the same thing repeated there. You don't find any such spatial or architectural logic in the way the columns are produced there, are kept in the Vittala temple there. So, I mean, there have been many other people also have been conjecturing about this, that one of the things that people say is that probably the artisans kept these rocks in there and kept on shaving away bits of the rock and sounding the note till they found the note that they want. That could be one way in which we did that. Now, I just want to point out that this whole idea of producing music from rocks is not a new thing. Okay, so if you go a few mountain ridges to the north of Hampi, you reach this spectacular, too many people don't see this. This is a megalithic graveyard, you could call it. It's a place called Hirebenakal, and it's a place where in the Iron Age, people commemorated the dead. Okay, so all these dolmens, as they call these megalithic structures, they look like stone huts. They were erected in memory of some dead people. And this entire region has got upwards of 1,000 megaliths, all of them not so spectacular, some of them are less spectacular. Closer up they look like this. Most of them are ruined because a lot of treasure hunters go there and dig around hoping that they'll find treasure below these things. It's a very spectacular site, and you can see that amount of stoneworking that has happened. So people build these large stone huts or dolmens or whatever, and then they use this rubble to kind of pack the outside of it, which is all fallen down now of course, so that the stones don't collapse outwards. And here, there's a very interesting thing here. This is again, there's a kind of landscape there with these perched rocks which weathering has produced, eons of weathering has produced. One of them looks very strange. It looks like somebody has sliced it like a fruit or something. So this one is called the Nagadi Gund. In the locals called the Nagadi Gund, because even today if you climb and hit it with a wooden club, it produces a ringing note that you can hear for a large distance around. So it looks very, I mean, to play upon imagery that we already have, it looks like the tolling of a bell when there's the death rituals happening or people are being laid to rest. It's also very spectacular setting, as you can see there, and you can see how nicely they finished it. There's yet another megalithic site east of this called Mallapur. So this place was inhabited by humans from prehistoric period, right from the early Stone Age. You can find vestiges down to these. This is in the Iron Age, roughly 1500 BC to maybe early first centuries of the Common Era. Here too there are a lot of megaliths, almost all of them are ruined. But near Mallapur, there is a temple, not a very spectacular temple, a small temple called Vanibhadreshwara temple. That's what the locals call it. But if you look at the place where Vijayanagara was founded, this it used to be known as Pampa Kshetra. Pampa is the river Tungabhadra, and this was a tirtha, which is, I mean, we know at least from 9th century there are records that were seen as a tirtha. So if you look at the work called Pampa Mahatmya, which is a Sthala Purana of that place, you find that there are these 8 guardian gateway kind of structures, places on all the 4 cardinal directions and the 4 sub-cardinal directions around Pampa Kshetra. This one is, in the text it's called Manibhadreshwara, and the locals have called it now Vanibhadreshwara. It's a very simple temple. We know that the temple was created during the Vijayanagara period, so this is another view of it. Okay, so Vijayanagara artisans have worked on it, even though today you have some really crazy kind of stuff happening on the upper part and all that. But this is also a later period structure, but within that you find the structure was created during Vijayanagara period. So we know that Vijayanagara artisans were active in this region. This region is also very spectacular in its thing. Somebody has tried to shape that boulder into a Nandi, and there's also, keeping with the times, there's also rock art of a dubious nature in the same vicinity. Yeah, but what's important here is that there is a lithophone, as they call it. Okay, these lithophones are these natural piece of rock. In this case, you know that this piece of rock has fallen away from here in some geological past, and somebody knocking around on it found that it creates music when you hit it on it. So what they've done is they've kind of made ground cupules or cup-shaped depressions in areas where it resonates. Okay, so if you strike there, it creates some. Lithophones are common all over South India. I mean, in many other parts of the world also you find it. But this way, generally, you find lithophone associated with the Neolithic. Neolithic is the late Stone Age. In South India, around 3000 BC to 1500 BC, you could say roughly. And lithophone, one of the characteristics is that they hardly, I mean, if this is lying on the bedrock, you can see that very little part of it touches the ground actually. So it's fallen in such a way that if you hit it, the whole thing is able to resonate. I'll just show you some, this one I hope, yeah. A small video I taken, it's not very clear, the sound is not that clear I think, so somebody has kept a small strike. I think there's another video which probably can tell you a little better. Certainly not a sound you associate with rock, right? So yeah, what I will do is I will just try to come out of the presentation. I'll show you another video which I think will give you, if you here I've used a slightly a more massive striker. I mean, if you don't see the video, you can imagine it's a bell, right? Okay, the point I was trying to make here is that it's definitely, I mean, it's definitely possible that the Vijayanagara artisans who were working on this temple would have definitely noticed the lithophone in the neighborhood. It's very close by. Most of the devotees go and bang on it, which is why it's currently in a very abraded condition. And in the near the temple, there's again one more stone which they seem to have tried to cut into this, that kettle drum like thing which you saw in Hirabanikal. So now there's a sort of pattern that you notice here. So the friend of mine who was working in Krishnagiri across the border in Tamil Nadu, in the Anchetti forest, so he sent me the picture of this curiously patterned rock, and he asked me, do you have any idea what this is? So on a hunch I told him, try striking it, it might be a musical rock, and he found that it was actually a musical rock. So this is found in abundance throughout. There's another thing I will just show you. All of you know Bannerghatta National Park. Apart from the wildlife and the safaris there, you also have a lot of megalithic structures in that region. So you have, these are the crude dolmens that you find in the region, and among them there's one particular rock which is currently lying on its side in a heavily degraded area, but this is how it looks like. So I'm fairly sure that if you put it in the right position on a rock, this thing, and bang it, this also would be a musical rock. So what I'm trying to say is that this idea of using rocks to generate musical notes or whatever is a very ancient thing. It comes right from and it's not just in India, you find it all over the world, these kind of structures. So why is it that you find it happening in the Stone Age and then later in the medieval period that people are trying to create musical sounds out of rock? One of the reasons is possibly that these people during the Stone Age spent a lot of their working life banging stone against stone, trying to knap stone tools and create other things which went into their monuments, like the one you saw in Hirabanikal. And also the medieval artisans, they were spending a lot of time just hitting rocks with chisels, and who better than them to understand what kind of properties that the stone would have. I'll end this talk here. I'll be happy to take questions along with others. Thank you.